Welcome to the 10th lecture on this series on tensor analysis. In the previous lecture, we had talked about four vectors in the special theory of relativity. Today I am going to continue on that theme. Today's focus will primarily be on force and acceleration in the special theory of relativity. To begin with, let me remind you that our prototype 4 vector in STR is a space-time 4 vector x mu, which has components x0, x1, x2 and x3. x0 is c times t, and the other three components make up the spatial part or x vector. Let me also remind you that if you differentiate x mu with respect to time, you do not get a 4 vector simply because time is not a scalar or an invariant under Lorentz transformations. In order to get a 4 vector, what you need to do is differentiate x mu with respect to the proper time tau. So u mu, the 4 velocity, is defined to be dx mu d tau, which from elementary calculus is equal to dt d tau times dx mu dt. dt d tau is our familiar factor gamma, 1 over square root of 1 minus u square by c square. And this leaves us with the result that the 4 velocity is gamma times the derivative of x mu with respect to time, which is c, comma, dx vector dt, and dx vector dt is our familiar 3 velocity u. So one important point, the spatial part of the 4 velocity is not the 3 velocity, it's the 3 velocity multiplied by the gamma factor. Let us now take a look at the next step, which is 4 acceleration. So in order to get the 4 acceleration from the 4 velocity, the idea should be exactly the same. You have to differentiate u mu, not with respect to time, but with respect to proper time. So a mu by definition is du mu d tau, and that of course is the same as before, that is gamma times du mu dt. So with the overall factor of gamma, what we have to do is differentiate u mu next. Now u mu's derivative of course has two terms, one in which gamma gets differentiated. So you have gamma dot times c comma u plus gamma times derivative of c comma u. Now the derivative of c is of course 0. And u's derivative with respect to time is our familiar 3 acceleration, the familiar acceleration in 3-dimensional world, a. In order to proceed further, we need to derive an expression for the time derivative gamma dot of the Lorentz factor gamma. Now, in order to do that, we start from the standard defining property of gamma, that gamma square is 1 over 1 minus u square by c square. And taking a logarithm of this expression gives us 2 log gamma plus log into 1 minus u square by c square. We are taking the logarithm simply so that the calculation of the derivative becomes simpler. If we now differentiate both sides of this equation, I am going to get twice gamma dot by gamma from log gamma. And from log of 1 minus u square by c square, I am going to get 1 by 1 minus u square by c square multiplied by the derivative of minus u square by c square. That of course gives us a factor of minus 1 by c square in the numerator here. But in addition to that, you are differentiating u square. Remember, u square is actually u dot u. So when you differentiate this, what you get is d dt of u square is u dot du dt plus du dt dot u, but because dot product commutes, you end up with twice u dot du dt, that is twice u dot a. So that is what you have up here. So this total thing of course is 0, the derivative of the right hand side. And this immediately tells us that gamma dot has to be gamma cube times u dot a by c square. The gamma cube comes simply because you are multiplying 1 over 1 minus u square by c square, which is gamma square, by 1 gamma, which was there already with the gamma dot. So this is the form that gamma dot takes, and when we substitute this back in our formula for a mu, we are going to end up with a compact form for the 4 vector components. The 4 acceleration works out to be gamma squared as an overall factor times gamma squared u dot a by c square. I've taken one extra gamma out of gamma dot because I've also had a gamma multiplying the second term, times c comma u plus 0 comma a, and when you add them all together, the 4 vector for acceleration, the 4 acceleration ends up with this particular form. Its temporal part is gamma to the 4 u dot a by c. The spatial part has a factor of gamma square times the actual acceleration in 3 dimensions a plus gamma square u dot a times u by c square. So you must appreciate that the 4 acceleration is considerably more complicated in form than the 4 vectors that we have met so far. There is, however, one frame in which the form of this 4 acceleration simplifies considerably. And that is the form in which the accelerating particle is instantaneously at rest. So if u is 0 in a particular frame, that of course is what is called the instantaneously co-moving frame or instantaneous rest frame of the particle. In that, u equals 0 would also imply that gamma is simply 1, and so the 4 acceleration will take this very simple form 0, a vector itself. So in the instantaneously co-moving frame, the 4 acceleration has a temporal part of 0 and a spatial part which is just nothing but the 3 acceleration. This is going to come in pretty handy in what is going to come. In an arbitrary inertial frame, however, the form of the 4 acceleration is, as you can see, rather involved. Because this is rather involved, it's a good thing if we could check out whether the calculation obeys expected results. One result that we expect almost immediately is this. Since the 4 velocity has a square or u upper mu, u lower mu of c square, which is a constant, it immediately follows from differentiation that u mu a mu must be equal to 0. In other words, the acceleration 4 vector must be orthogonal to the velocity 4 vector. Let us just check whether that is true. What we have here is a form for the acceleration 4 vector, and when we dot it with the velocity 4 vector, which remember is simply u mu equals gamma c comma u vector, what we are going to get is the following. U mu a mu will have an overall factor of gamma cube from gamma square from a mu and gamma from here, and then you are going to multiply the 0th components together, so gamma square u dot a by c will be multiplied by c, and from that you are going to subtract the dot product of the spatial vector, so u dotted with this. This looks like a pretty complicated expression, but note that you have u dot a which you can take common out from every one of these terms, and so you get gamma cube times u dot a, then you get a gamma square from here, minus 1 from this u dot a, and a minus gamma square into u square by c square from this last dot product. So if you take this term and this term together, you get gamma square into 1 minus u square by c square, which is obviously 1, and you're taking away 1 from that, so this entire thing cancels and you end up with 0. So at least one of the basic properties that we demand of the 4 acceleration checks out. It is orthogonal to the 4 velocity. What about the norm or square of the acceleration vector? If I form a mu, that's not really very complicated. All you have to do is square the temporal part and subtract from that the square of the spatial part, or square of the spatial part vector, that is its dot product with itself. So this is what you are going to get from there. Now this expands out into a rather formidable looking expression. This a becomes a square, then this twice ab term gives you this quantity, because you are going to do a dot product of a with u and the factor of 2, which is always there in the 2ab term. And then you have gamma to the 4 u dot a whole square, u square by c to the 4. This still looks pretty complicated, but if you look at this carefully, what you see is you have a minus a square here. If you combine the first term and the last term, what you are going to get is gamma to the 4 u dot a whole square by c square times 1 minus u square by c square. And that cancels 2 powers of gamma, and you are left with gamma square into u dot a whole square by c square. You have minus twice that here. So overall, what you are going to get is a minus gamma to the 4 a square plus gamma square u dot a whole square by c square. The upshot of all this is a upper mu, a lower mu, the square of the vector a turns out to be negative. That of course is not surprising. Remember, our metric is an indefinite metric. We have plus, minus, minus, minus in the metric. And what this really means is that it is possible for you to have a negative square for a vector or a zero square for a non-zero vector. Indeed, this leads to one way of classifying 4 vectors. A 4-vector V is called time-like if its square, V upper mu, V lower mu, is greater than 0. Let me just remind you that if V upper mu happens to be V0, V vector, then V lower mu, the covariant version or 4 covector corresponding to V, has components V0 and minus V vector. So V upper mu, V lower mu really is term by term multiplication of these terms summed up, and so that is actually given by V0 square minus V vector square. This of course is something we have already used a while ago. If this quantity is positive, that means the V0 term dominates, has a larger size, so it's natural to call this time-like. Similarly, if this is negative, then the spatial part, the size of the vector V, dominates over the magnitude of V0. So V upper mu, V lower mu less than 0 defines what is called a space-like vector. And finally, a null-like, also known as light-like 4 vector is one for which the inner product with itself is exactly equal to 0. So, among the 4 vectors we have met so far, u mu and p mu are time-like. Remember, u mu has a norm squared, u upper mu, u lower mu, of c square. For p upper mu, p lower mu is m square c square. These are both positive quantities, so these are time-like 4 vectors. A mu, as we have just seen, is space-like because it has a negative square. In fact, this last result should not come as a surprise because there's a general result which is very important about 4 vectors. A vector orthogonal, here when I say vector, in this class we will mean 4 vectors unless otherwise specified. A 4 vector orthogonal to a time-like vector is either 0 or space-like. Of course, if a vector is 0 and you dot it with any vector whatsoever, the result is going to be 0. So a 0 vector is orthogonal, so to speak, with every vector. But if the vector is not 0 and it is orthogonal to a time-like vector, then it is space-like. Now, let's just give you a proof of this result because this is going to be very useful later on as well. Now, if V is time-like, that means V squared, V's inner product with itself is positive, that immediately tells you that V0 square is bigger than V square. So that of course is what time-like means. The time part dominates. Now if V is orthogonal to W, that is V mu W lower mu is 0, Or in other words, v0 w0 minus v vector dot w vector is 0. That means, of course, v0 w0 equals v vector dot w vector. Now notice that if we have a time-like 4 vector, then v0 cannot be 0. v0 square has to be bigger than v square, which of course is a positive number. So I can safely divide by v0 and say w0 equals v dot w by v0. Now, that tells you that w0 squared, the temporal part of w squared, is given by v dot w whole squared, v vector dot w vector whole squared by v0 square. And a very standard property of the dot product, which you can call the Cauchy-Schwarz inequality if you want to sound fancy, but which simply means that cosine of theta is never bigger than 1 in size, tells you that this quantity has to be less than or equal to v's magnitude squared times w's magnitude squared in the numerator, divided of course by v0 square. Now since v0 square is larger in size than v square, this has to be smaller than w square. So for the vector w, the temporal part has to be smaller in size than the spatial part. The exception, of course, is when w vector is actually itself 0 and w0 is also 0. But other than that, w has to be space-like because it has a larger sized spatial part than its temporal part. So the fact that a mu is space-like, the 4 acceleration is space-like, is not a surprise. 4 velocity having a constant invariant square implies that 4 acceleration has to be orthogonal to 4 velocity, and because 4 velocity is time-like, 4 acceleration has to be space-like, as we had pointed out. By the way, there was a much easier way of figuring out that a mu is space-like than do the whole calculation that we did a while ago. Remember that in the rest frame or instantaneous rest frame of that particle, the 4 acceleration takes the simple form 0, a vector, where this a is of course not the acceleration in the original frame but the acceleration in the instantaneous rest frame. In order to distinguish that, let's call that a tilde vector. The tilde is there simply to remind you that this is not the acceleration in any frame but the acceleration in the instantaneous rest frame. Now in the instantaneous rest frame, if you calculate a upper mu, a lower mu, you would obviously get minus a tilde vector whole squared, which obviously is a negative quantity. So, in the instantaneous rest frame, the norm of a whole squared is negative. But since the norm of a whole squared is an invariant quantity, it is the same in all frames. So in each and every frame, the norm of a whole squared is minus a tilde vector squared. So that's negative. Of course, that's not the same as the expression that we had worked out here. Not the same expression, I mean. But of course, this a is the acceleration in a frame in which the particle's velocity is u. So basically what you are saying here is this. A tilde vector squared has to be equal to gamma to the 4 a square plus gamma square u dot a whole square by c square. This is also a result which is useful, as you will see later. Let us now come to the concept of 4-dimensional force. In 3D, force is a pretty familiar object, and we define force in 3D simply by rate of change of momentum with time. Now the corresponding 4-dimensional entity, of course, is p mu. So we would like to differentiate that to get a 4 vector. But as we have already seen, differentiation with respect to time will not do. So we define the 4 vector k mu by differentiation with respect to proper time, d tau. Since p mu is given by mc gamma, m gamma u, remember mc gamma is simply E by c, energy divided by the speed of light. and m gamma u is a 3 momentum of the point particle whose mass is m. Differentiation immediately leads to k mu being given by this. K mu is not dp mu dt as written here, it has to be dp mu d tau. That's actually dp mu dt times dt d tau, but that times dt d tau is an extra gamma. So we have gamma times derivative of this p mu with respect to time. So gamma times 1 by c de dt, comma, dp dt. And dp dt, of course, is our familiar three-dimensional force. So this is what the 4 force k mu is. Its temporal component is gamma times 1 by c de dt, and its spatial component is gamma times the force F. Now, since p mu, like u mu, has a constant or time-independent square, p upper mu, p lower mu is m square c square, this immediately tells us that p mu k lower mu, the dot product between p and k, has to be equal to 0. Therefore, k mu is orthogonal to p mu, and that gives us another way of writing the temporal component of k mu, which is pretty useful in applications. If I just use the fact that k mu has to be orthogonal to p mu, this gives rise to the result E by c, which comes from p mu, times 1 by c de dt, which apart from the factor gamma is k mu's temporal component, minus p vector once again from p mu, dotted with f. Of course, you had gamma f, but there's an overall factor gamma anyway, and since this result is 0, you can always divide through by the gamma to still get 0. This tells us that 1 by c de dt, the quantity which is sitting here, is actually equal to f dotted with the momentum m gamma v divided by the quantity E by c. F dot p is of course f dot m gamma v, and E by is mc square gamma, so E by c is m gamma c. The m gamma cancels and you are left with f dot v by c. So that is what is going to sit in the temporal part of the 4 force k mu. Taking this into account, our form for the 4 force can be written in this particular manner. K mu has a temporal part which is given by gamma times f dot v by c, and a spatial part which is gamma times f. At this point, let me remind you of a question that we had raised in the last lecture. When we talked about the 4 momentum p mu, what we had was p mu had components given by m gamma c times m gamma v vector. Now the spatial part of this 4 vector is what we had identified with the momentum p. At that point I raised the question, why don't we just say that the momentum is still p and the spatial part is just gamma times p. Note that that's exactly what we have done here. We have not defined the force, the 3 force, to be the spatial part of the 4 vector k mu. We have defined the 3 force to be dp dt, so that the spatial part of the 4 force actually has an extra factor of gamma. If we had adopted the same extra factor of gamma here and written this quantity as gamma times p, I would not have to worry about changing the definition of momentum. I would not have to worry about things like relativistic mass and so on. But the reason why we insisted that the entire spatial part of p mu has to be called the momentum is very important. Let me just remind you of what we said in the last lecture. We have a law of conservation of momentum and we want to ensure that that survives into this transition to relativistic physics. So one thing we can always demand is that total fourth momentum p mu be conserved. And that law, if correct at all in one frame, would be correct in all frames, being a vector equation. Being a vector equation ensures that this particular law passes the basic test of the special theory of relativity. To be a law of physics, an equation has to be equally valid in all inertial frames. If total force momentum is conserved, then so is the spatial part. So it's the spatial part of the total force momentum which is going to be conserved, not the total m times v. Which is why we abandon the notion that m times v is the momentum and consider the entire spatial part of p mu to be the momentum. You might very well ask, why don't we do that here as well? Why don't we just consider the entire spatial part of k mu to be the force? What we have done is we have stuck to the old Newtonian definition of the force, not redefined that. We have just said force is dp dt, the time derivative of the momentum. One important point is there is no experimental way to distinguish between this possibility that gamma f is the spatial part of k and the possibility that f is the spatial part of k. At least not from low velocity experiments, because at low velocities gamma is 1, so you cannot distinguish between the two. So classical pre-Einsteinian physics does not come to our rescue here. Neither is there any conservation law which demands that one of these objects should be defined specially over the other. Of course, you might just say this is a matter of definition, and we can just as well define dp dt to be the force. But remember, Newton's second law has physical significance because it's more than just the definition of a force. dp dt is not just the definition of force. dp dt is equal to the force. The force can be calculated using other laws. For example, if you're talking of a charged particle in an electromagnetic field, you know that the force is Q into E plus V cross B. The question would be, is that equal to dp dt? Or is that equal to gamma times dp dt? The answer has to depend on experiments done at high velocities. And it is an experimental fact which tells us that what we consider to be the force, things like the terms given by Lorentz force law, is actually dp dt. So what we have done here is the correct thing. In what is going to follow, we are going to move away from the world of 4 vectors and 4-dimensional objects and concentrate on the relationship between two distinct 3-dimensional vectors in special theory of relativity, the relationship between force and acceleration. I hope that by the end of the discussion, you would also realize why I was so against the notion of relativistic mass in my last lecture. So F is dp dt, rate of change of momentum, in both classical physics, that is pre-Einsteinian physics, and in Einsteinian physics. In pre-Einsteinian physics, at least for a point particle, this reduced simply to mass times acceleration. We already expect the formula, the dependence to be more complicated in the case of relativistic physics, because instead of a constant prefactor m, you have m times gamma, and gamma of course depends on the velocity and hence through that on the time. So let us see what comes out of this. When we differentiate m gamma u with respect to time, you actually end up with two terms. The first term is simply m gamma times du dt. That is the relativistic mass m gamma times the acceleration. But you also have another term m gamma dot times u. And we had already calculated what gamma dot is a few minutes ago. So using that, we end up with this expression for force. Force is mass times gamma times acceleration plus m gamma cube into u dot a times u by c square. This gamma cube into u dot a by c square is of course none other than gamma dot. So you would all agree that the relationship between force and acceleration is definitely more complicated in relativity compared to the corresponding relationship in pre-relativity physics. Now, despite that, in one situation, this expression becomes rather simple. That is the case when u, the velocity, remember this is the 3 velocity we are talking about, is perpendicular to the acceleration. This is called, for obvious reasons, the transverse case. And there is a very simple situation where you get this. For example, when a particle is moving in a circle, its acceleration, of course, is along the radius, is centripetal, and the velocity is along the tangent of the circle, so the two are definitely perpendicular to each other. So in such a case, the second term in the expression above drops out, u dot a being 0, and f simply becomes m gamma a. In this case, the force is some kind of mass into acceleration, and this some kind of mass is actually nothing but m times gamma, which is the same as a relativistic mass. But in this particular context, we call this the transverse mass mt. So when the velocity and the acceleration are transverse, force is proportional to the acceleration with a proportionality factor of mt. The other situation where the formula simplifies is when u is parallel to a. If u is parallel to a, then the quantity u dot a times u can be easily seen to be the same as u squared times a vector. And what that means is incorporating the second term, adding it to the first term for force becomes pretty straightforward, and force now becomes m gamma into 1 plus gamma square into u square by c square into a vector. A small amount of algebra will show you that the quantity in the brackets 1 plus gamma square u square by c square is nothing but gamma square. So for this particular case, where u is parallel to a and the motion is longitudinal, the force is given by m gamma cube times a. So the factor m gamma cube is what you call the longitudinal mass, ml. Note that once we decide to move away from considering mass to be the inherent property of a particle, something which is an invariant and does not change from frame to frame, and decide to use masses which are well suited for our particular purpose, especially for the purpose of retaining older equations in their original form, we are on a slippery slope indeed. This mass that I just talked about is what used to be called the rest mass, but today we will just call it a mass, and that's the one mass that we should use, the quantity that I've written m here. On the other hand, if we want to adjust our definition of mass according to our needs, we will end up with several definitions of mass. For example, we already have met the relativistic mass in the last lecture. I am denoting that mr here, although in older literature, this is exactly what would have been called m. And our m would have been called m0. The relativistic mass mr is the ratio of p and v. So all you are saying is instead of the formula being p equal to mv, it will become p equal to mrv. We rescue our old formula at the expense of having a more complicated expression for the mass. If things had stopped there, then maybe using relativistic mass would not have been too bad a thing. And we would of course have the advantage of being able to express the best known equation in physics of all time, E equal to mrc squared, in a simpler form, the one which everybody knows and loves, E equal to mc squared. However, to us the notion of mass is more connected to inertia, the opposition which a body offers to being accelerated. Now in that context, we see already that we have different versions of mass depending on the kind of motion we have. If the motion is transverse, that is the acceleration is perpendicular to the velocity, we end up with a ratio between f and a which is equal to m times gamma. This is the transverse mass which happens to be equal to mr. But on the other hand, for longitudinal motion where velocity and acceleration are parallel, we end up with an entirely different, indeed larger, value for mass, so called the longitudinal mass m gamma cubed. Indeed, the fact that the transverse mass happens to be equal to the relativistic mass only adds to the confusion, because sometimes if you are just looking at motion in a circle, you would be tempted to think that the relativistic mass is all you ever need. And of course, if the motion is neither transverse nor longitudinal, that is, the acceleration is neither parallel to the velocity or nor perpendicular to it, but somewhere in between, the relationship between mass and acceleration is way more complicated. We are going to focus on this particular relationship now, but before that, let me just say my final 2 bits on the issue of all this plethora of masses. All this would not be necessary if the only mass we ever used is the rest mass or the invariant mass m, and did not worry about writing down equations in a much simpler fashion. As we have already said, once we go over from the flat spacetime of special relativity to curved spacetime of general relativity, the relativistic mass concept becomes even more unwieldy to use, so we are not really going to use that any longer. Let us now focus on the relationship between force and acceleration in general.
For the time being, we are going to move away from the 4-dimensional world of 4 vectors, 4 forces and 4 accelerations, and stick to the 3-dimensional world of 3 forces and 3 accelerations. What I am also going to do is do away with the summation convention temporarily. I am going to explicitly write a sum over spatial components right now, as and when necessary. So, what we are going to do, of course, is go back to the relationship that we had derived a while ago between force and acceleration, namely this one. Force is mass times gamma times acceleration plus m gamma cube times u dot a times u by c square, and write this equation in terms of its spatial components. The ith component of this equation simply becomes the following. Fi is m gamma times ai plus m gamma cube. Now you have this u dot a, which is sum over j going from 1 to 3 of uj aj, and then of course you have the ith component of u by c square. Now what we want to do is write this as a relationship between force and acceleration. So the jth component of the acceleration can be related to the ith component of the force. And it's very easy to do. The second term is already in the form where aj is actually sticking outside. The first term, which has ai, can be converted into a term with aj simply by using delta ij. So what we have is the ith component of the force is sum over j going from 1 to 3 of m gamma delta ij. That's what will give you the m gamma ai after summation over j, plus m gamma cube times ui uj by c square. So what we see is that instead of getting fi is m times ai, you get something which looks at the face of it a lot more complicated. However, all this is really telling you is that fi is actually of the form sum over j going from 1 to 3 of mij aj. That is, instead of a single number m, the mass, what you have is a mass matrix or a mass tensor. In other words, the way in which the force is related to the acceleration in special theory of relativity can be written in a simple matrix form given by the following. You can write the components of the force F1, F2, F3 in a column vector. A1, A2, A3, the components of the acceleration, also goes into another column vector, and the relationship between these two column vectors is not just F is a simple number times the acceleration column vector, but F is some matrix or so-called inertia tensor acting on the acceleration to give you the force. So what I've done here is explicitly write down the form of this mass tensor. The form may look complicated, but we already know that is because we have written this down in an arbitrary coordinate system. For example, if we had chosen our coordinate system in such a way that the velocity of the particle were entirely along the, say, the x-axis, then this matrix would simply look like the following. M gamma, of course, is an overall factor, and then you will have 1 plus gamma square beta square sitting here. This would be 0, 0, 0, 0. And then you would have 2 1s. The simple form obviously makes it clear that in the case of such a situation, the force is related to the acceleration by force F2 equal to m gamma A2 and F3 equals m gamma A3. Remember, these are two components which are perpendicular to the velocity, so they correspond to the transverse mass scenario. What about relationship between F1 and A1? That is also pretty straightforward. And using the fact that 1 plus gamma square beta square is actually equal to gamma square, we get m gamma cube A1. Again, showing you the fact that the longitudinal component of the force, the one parallel to the velocity, is related to the longitudinal component of the acceleration by this factor m gamma cube. However, we cannot usually use this special coordinate system all the time simply because the direction of the velocity might keep on changing as the particle moves, and so unless we are ready to switch coordinate system every time the particle changes direction, we will have to use the full-fledged mass tensor. And in order to find out the acceleration, we would actually have to invert this relationship. Now that sounds like a tall order because this looks at the face of it like a complicated 3x3 matrix. However, the fact that it takes such a simple form for the special case that we talked about gives us hope and tells us that we can actually invert it with little difficulty. That is what we are going to do next. Indeed, the approach towards inverting this relationship is pretty straightforward. All we have to do is break up the force into a component parallel to the velocity and one perpendicular to the velocity, and then use the fact that the relationship between force and acceleration is well known in these two special cases. So, elementary vector analysis tells us that we can break up the force F into a component which is parallel to the velocity, F parallel, and another component perpendicular to the velocity. And the way in which you find out these components is straightforward class 12 level vector analysis. The component parallel to F is given by F dot U times U vector by U square. That of course is the projection of F in the direction of U. And to that you have to add whatever you get when you take this away from the force. So that gives you the F perpendicular. So the first term on the right is your F parallel, the second term is F perpendicular, and the acceleration can be written down immediately because we know that for F parallel, the contribution to the acceleration will be F parallel divided by the longitudinal mass, m gamma cube, and F perpendicular will have to be divided by the transverse mass. And the net acceleration will simply be the sum of these two terms. So, we can put all of these together and write acceleration is 1 by m gamma cube times F parallel plus 1 over m gamma times F perpendicular. Now, we can put them together with a small bit of manipulation, and after some rather trivial algebra, the form of the acceleration in terms of the force actually becomes pretty simple. It is just 1 by m gamma times f minus f dot u into u by c square. Note that this is a c square here, not an u square. So this quantity is not really f perpendicular as it might look like. The ultimate upshot is the final formula is rather straightforward. And if I write this in terms of components, ai simply becomes 1 over m gamma times fi minus, once again, f dot u is sum over j from 1 to 3 fj uj times ui by c square. And now I can write ai in terms of fj, that is, we can write an inverse mass tensor m inverse ij times fj, giving you ai, and that inverse mass tensor actually ends up having a rather simple form. M inverse as ijth element turns out to be 1 over m gamma delta ij minus ui uj by c square. To summarize then, the ith component of the force Fi is given by sum over j equals 1 to 3 mij aj. So that's the mass tensor for you, and the inversion of this relation gives you ai, again sum over j going from 1 to 3 of m inverses ijth element acting on fj. Now, these matrices turn out to have rather a compact form. Mij we have already met earlier. Mij is m gamma times delta ij plus gamma square beta I beta j. If anything, m inverse has an even simpler form. M inverses ijth element is 1 over m gamma delta ij minus simply beta I beta j. Just in case this seems too simple to be true, let us just point out that you can immediately check whether this is correct by multiplying the two matrices m and m inverse. So the ijth element of the product of m and m inverse is simply mik m inverse kj summed over k. If I now just plug in the expressions that we have, the m gamma and the 1 by m gamma obviously cancel, and we have this particular sum over k. Delta ik plus gamma square beta I beta k times delta kj minus beta k beta j. Now when you multiply out the brackets, you get 4 terms, and the summation over k makes these terms very, very simple. The first one, delta ik delta kj, of course sums up over k to give you delta ij. Then you have gamma square beta I beta k delta kj summed over k makes it gamma square beta I beta j, and so on. It's a pretty straightforward calculation, and if you carry it out through, it's pretty straightforward and you end up with delta ij, which does verify that these two matrices m and m inverse are really inverses of each other. So the job of expressing the acceleration in terms of the force, or vice versa, in special relativity is actually pretty straightforward. We have been able to explicitly write down the expression for acceleration in terms of the force, and then, given an arbitrary force law, we can use this to find out the acceleration, and from there solve the kinematics of the problem. Let me wrap up today's lecture with an explicit calculation for a particularly familiar problem. Now, the most common problem which you would find in most relativity textbooks involve what is called uniform proper acceleration. Now, that is a very important topic, especially because it allows you to sort of have some insight on what happens when you move away from inertial observers to non-inertial observers in special relativity, and from there on to the special situation that arises when you have gravity and space-time curvature. So that would be a sort of stepping stone towards general relativity. But that is a very important topic in its own right, and we are going to discuss it in some detail in the next lecture. Today, the example that I'm going to talk about is a very simple one, that of a projectile moving in 2 dimensions. A very familiar problem from class 12, but this time we are going to assume that the projectile is moving fast enough the relativistic effects become important. So our setup is as follows. We have an electron which is projected between two capacitor plates. Capacitor plates are uniformly charged, and I have deliberately drawn the positive plate below in the picture so that when the electron is projected upwards, it gets bent down by the force and ultimately comes back to the plate. The questions that we can ask is, how high will the electron travel between the plates? How long will it travel for? How far will it go? And so on. These are all standard questions that we are used to asking for projectile motion. So the setup here is exactly the same as projectile motion, but note that I am not saying that this is a particle moving under gravity, because there, especially at very high speeds, complications because of general relativity might very well arise. Here this is a purely special relativistic problem, no gravity involved. The force which is dragging the electron down is nothing but electrostatic force. Now, this force, of course, has only one component, the y component, a negative one. So the force takes the form 0 minus qv 0. And just to remind you, this automatically means that k mu, the 4 force, is going to have these 4 components. There will be an overall factor of gamma. The spatial part will be 0 minus qv 0, whereas the temporal part is going to be f dot v by c, and that is going to work out to be minus qe vy by c. So let us go back to the 4 velocity and 4 momentum again, and remember that dp mu d tau, which is k mu, is gamma times dp mu dt. So apart from the overall gamma factor, this is what you are going to get. And this can immediately help us write down 3 distinct components for the equations. Actually 4, but there is no role that the z component plays here. So we are just going to stick to the time component and the x and the y component. The time component equation simply becomes ddt of mc gamma or ddt of e by c is minus qe vy by c. Well, the other 2 components are pretty straightforward. ddt of mvx gamma is 0 and ddt of mvy gamma is minus qe. Note that I have gone back to the components of p mu because they actually give us easier equations to handle in this case. In principle, I could have just used the equations that we had derived a while ago relating acceleration to force and gone from there, but this is actually easier to calculate with. Now, one of the first things you should note is that these 3 equations are not really independent equations. In fact, if I take the second and the third equation, multiply them respectively by Vx and Vy, we will actually, after a bit of manipulation, end up with the first equation itself. So, there are really 2 independent equations out here, but writing them as 3 equations makes life a bit easier, as you will soon see. Now, these equations are pretty straightforward. Indeed, the first one just says that the rate of change of mc gamma, which is essentially the energy up to a factor of c, is minus qe by c dy dt, and that integrates trivially to the result mc gamma minus gamma 0 minus qe by c into y. You should recognize that this is nothing but a relativistic version of the work energy theorem. The total energy of the particle has gone down simply because the particle has climbed up and done some work, which is minus qey. mc squared times gamma minus gamma 0, note, is nothing but the change in energy of the particle. Since the rest energy of the particle is fixed, it's really the change in the kinetic energy. Standard work energy theorem that we also had in pre-relativistic physics. And the other 2 equations, which essentially talk about components of the momentum, are really rather trivial to integrate. ddt of mvx gamma being 0 immediately integrates to Vx gamma being equal to Vx0 gamma 0. Here, of course, Vx0 and Vy0 are the initial values of the components of the velocity of the electron, and gamma 0 is the initial value of the gamma. Very similarly, integrating the y component equation simply gives rise to Vy gamma is Vy0 gamma 0 minus QE by m into t. Note that QE by m is what would classically have been the acceleration of the particle under these forces. So that is what I am writing as A tilde. So we end up with three equations, one relating the change in energy with y, the other two essentially giving us Vx and Vy as functions of time. Now a bit of simple manipulation will help us to get rid of gamma from these expressions. All we need to do is square and add the two equations for Vx gamma and Vy gamma. And if we do that, carry out the algebra a bit, we will end up with gamma as a function of time directly. So gamma works out to be gamma 0 square minus twice A tilde, remember that's our acceleration, Vy0 gamma 0 t by c square minus A tilde square t square by c square. That's the square of gamma, of course. Gamma is the square root. Now this tells us what height a particle achieves at a given time simply by using the fact that y of t is mc square by qv times gamma 0 minus gamma. Plugging in the value of gamma that we have as a function of time, we do end up with y as a function of time here. Now just to check whether this is actually consistent with what we already know, let us consider the situation where the particle is non-relativistic. That is, Vx0 and Vy0 are both much smaller than c, and hence gamma is almost equal to 1. Note that under such a situation, yt simply becomes c square by A tilde, the gamma 0 being replaced by 1, and then you have 1 minus the square root, which we can expand binomially. Even within the square root, the gamma 0s have been replaced by 1, and we just have the Vy0 and A tilde, which are both small quantities, and using the binomial expansion and a bit of simple algebra gives us a familiar formula for y of t. Y of t equals Vy0 t minus half A tilde t square, which is of course our standard projectile formula from class 12. Now that we have the solution, we can of course answer several questions like how long does the electron climb, or what is its time of flight. Now to find out how long it climbs, that is at what time does it reach maximum height, all you have to do is equate Vy to 0, and that immediately gives us a result that the time to reach maximum height is gamma 0 times Vy0 by A tilde. Let me point out once again that for the low velocity limit, this agrees perfectly well with our well-known result that time to reach maximum height is given by Vy0 by the acceleration. Here there's an extra factor of gamma 0, but what may be a bit surprising is that the gamma that you have here is the initial gamma for the particle. So the time of flight is enhanced because of relativity, gamma being a factor, which is always more than 1. Time of flight, for that you have to equate y to 0, that is, you have come back to the original height, and it's pretty easy to see that it's nothing but double of this result that we have already obtained. Once again, something very familiar, but with an extra factor of gamma 0. What is the maximum height reached? Well, all you have to do is take this value of t, plug it back into the expression for y of t, and you end up with this expression. Maximum height reached is c square gamma 0 by A tilde into 1 minus square root of 1 minus Vy0 square by c square. Now, when Vx and Vy are much smaller than the speed of light, once again we are back to our non-relativistic limit. It's pretty easy to use binomial theorem and show that this height expression boils down back to Vy0 square by twice A tilde, which is of course a familiar v square sine square theta by twice g formula that we had in projectile motion. Now there are many questions that we can ask. For example, we can integrate dx dt, which is gamma 0 vx0 by gamma of t. And here, gamma 0 and vx0 are fixed quantities. Gamma of t is a known function of time that we have just worked out. So integrate this to find out x as a function of t, and in particular, try to figure out what is the relativistic expression for the range of the projectile. You would expect the range to be enhanced because of the simple fact that since gamma is decreasing as the particle climbs up, gamma Vx being a constant means that the velocity in the x direction actually increases as long as the particle is climbing up. It actually decreases back to the original value of Vx0 when the particle returns back to the same height it started out from. But in between, unlike the case of non-relativistic projectile where Vx is constant throughout, Vx actually takes a value which is larger than the value it initially had. Hence, and given the fact that time of flight has also increased because of the extra factor of gamma 0, coupled with this additional velocity in the x direction, we expect the range to be larger. It is an interesting question to examine how much larger and compare the relativistic result with the non-relativistic one. I will leave that as an exercise for you. In the next lecture, we are going to take a look at motion with uniform proper acceleration, whatever that means. But before that, we will have to take a look at certain other quantities like exactly how does acceleration transform when you go from one frame to another, and then go on to talk about the application of 4 vectors and 4 tensors to the theory of electromagnetism in special relativity. Until then, bye.